Let me just say before I start a few words about GRSS. I'm actually in the society. I am the Director for Global Activities, which sounds like an extremely important and prestigious title, but what it really means is that I'm responsible for going around the world to the extent that I can and finding people who are interested in joining. So I'm like a recruiter, shall we say. But from my perspective, what's important about GRSS is interconnectedness between people within a community and in other communities around the world. And I would say that it is really an excellent opportunity for you as students to get involved in something bigger than yourself and even bigger than your academic life. We offer a lot of different opportunities. I don't want to spend much time today talking about it, but if you were to form a chapter, you would have resources, people resources, such as your faculty mentors, resources in people around the world who are willing to help you, come here and talk with you, and even some amount of funding for doing student projects. So if you have initiative and you feel that need to connect, we would welcome you greatly. So that's all I'll say about GRSS. I'm happy to talk with you about it after this talk. I'm here today to talk with you about the NISAR mission, NASA-ISRO Synthetic Aperture Radar Mission. As Dr. Rajan said earlier, we've been building this for almost 10 years now, jointly between NASA and ISRO. I work at the Jet Propulsion Laboratory, where we are building the US components. And it's been a long ride, and we are finally getting ready to launch this system early next year. So that's why the title of my talk is The Final Stretch Towards a New Capability for Earth Science and Applications. Before I get started, I just wanted to put it in context of the overall NASA program in Earth system science. You can see this rotating globe showing products that are created on a global scale from NASA satellites, generally at fairly low resolution, but comprehensive coverage obtained as quickly as possible to allow us to look at all the processes that are occurring and how they evolve over time. There are 6 primary focus areas that NASA has divided their Earth system science approach in. That would be atmospheric composition, carbon cycle and ecosystems, climate variability. You can read the list on the left. The NISAR mission, which I'm about to describe, actually has applications in 5 of the 6 focus areas at NASA. Synthetic aperture radar is a very powerful tool, allowing us to look at carbon cycle, climate through ice characterization, Earth surface and interior, and water and weather. I'm not going to say much about this, but NASA has a very large constellations of satellites going all the way back to the 90s and before. The ones in the 90s, many of them are still operating. Terra and Aqua, you can see here back in 2000, are still working very well and providing many of the data sets you saw on the previous page. NISAR is here, getting ready to launch, and NASA's program continues into the future. Both free-flying satellites, cube satellites, and instruments that fly on the International Space Station. So it's a very comprehensive program in Earth science. So back in 1978, JPL was the first institution to launch a synthetic aperture radar. I'll tell you what that is in a minute, so in case you don't know. And this lasted, unfortunately, only 3 months in orbit. But in those 3 months, it acquired new data sets that the science community had never seen before, over oceans, over the cryosphere, over ice sheets, over land. And these data sets formed the basis for almost all of the science measurements that we are making with NISAR and many other synthetic aperture radar missions. This was a really important and watershed mission. So it's been since 1978 that we at JPL and NASA have been trying to fly yet another free-flying synthetic aperture radar mission. And it's taken our partnership with ISRO to be able to make that happen. I could talk for hours about why that's the case. I don't have time, so I'll just leave it at that. So NISAR came from a process called the Decadal Survey in the United States. This is something where the scientists get together on a decadal scale, hence the name, and they make recommendations to NASA about what NASA should be doing in the upcoming decade. And back in 2007, there was a recommendation for a mission similar to NISAR, which could address, using synthetic aperture radar, three main science disciplines. The top three here: dynamics of ice, looking at ice sheets, mountain glaciers, and sea ice, trying to understand the interaction of the ice sheets with the atmosphere, precipitation with the oceans, and understand what that meant for climate. Ecosystems and biomass change, primarily looking at woody biomass above ground and how what the carbon content of that biomass is and how that carbon content changes over time due to either natural change or human-induced change. The third area is solid earth deformation, looking at earthquakes, volcanoes, landslides, other kinds of surface deformation processes that create hazardous conditions for humans on Earth. These were the three main science disciplines that were identified by the Decadal Survey. It turns out that synthetic aperture radar can address aspects of all of these and many, many other disciplines as well. So that was 2007. It took a long time for us to find the programmatic ability to make it happen. And it wasn't until around 2011 when I made a trip to India and talked with some people from the space agency about a possible partnership that we actually started to have a partnership. And this partnership with India is completely enabling. I think both countries could not have done a mission of this scale very easily without each other. So when we talked with India, with ISRO, they identified the same kinds of science questions that our scientists were interested in. So the top three you see here are common science objectives. In addition, India's remote sensing program, as I'm sure you all know, is highly focused on societal benefit and applications. So they have a focus on not just looking at the science, but converting that into useful, beneficial applications over India, as well as adding additional targets, shall we say, such as coastal ocean processes and also the oceans themselves. So with this suite of science questions, we have formed the NISAR mission. I'll say more about what these pictures mean as we're coming up. So since I know many of you probably don't know anything about synthetic aperture radar in detail, the first part of this talk is an attempt to make it a little bit more approachable through a series of animations. So hopefully this will be interesting to you and you can see them in this display. So the first animation I'm going to show you is just what the spacecraft looks like. I love this because the spacecraft is really impressive to me. I hope it's impressive to you. This is a custom-made spacecraft. Parts of it were built in the United States, parts of it were built in India, and together they form a very powerful system. So let's see if I can stop this. So what you're looking at right now, looking along the solar panel, the spacecraft bus is over here. You can see my pointer? Yeah. The spacecraft bus is provided by ISRO. It provides the control of the orbit, the propulsion, and it provides the power. here in this octagonal cylindrical structure is all of the electronics of the system. There are actually two radars in this system, one at a 24 centimeter wavelength, like that, which is at L-band, and one at 9 centimeter wavelength, which is called S-band. So NASA's providing the L-band system, the electronics, this entire structure, this boom that's going up here, and the reflector that's up at the top of that boom. That's all provided by NASA. ISRO is providing the S-band electronics that mount on this structure, as well as the spacecraft and the launch vehicle. So it's quite the intricate partnership between the two agencies. Let's just see if I can show you the reflector here. So the reflector is also quite impressive. There you can see it is a 12-meter deployable antenna. So this very, very large structure, about the size of this room, has to fit into the spacecraft fairing at launch and then be deployed to create this umbrella that can be used as a radar system. This animation is going to show you that deployment sequence to create the system in space. So we're flying in now to Sriharikota, where the launch facility is. We're actually using ISRO's GSLV launch vehicle number 2, GSLV-2. This is an animation. It looks real to me, but it's actually just simulated. That we will be launching at 6 p.m. Sometime after the end of January next year, probably most likely around March or April. That's not entirely fixed yet because we're still in the development phase, but very close to then. And we will launch into our orbit and take data, start taking science data something like 90 days after launch. So here we are launching. And it'll go pretty much straight to orbit. You'll note that whole system fits within that 4-meter launch fairing. After we get into orbit, the fairing separates, and we can then see the system in its stowed phase. So here you see the reflector. It's been collapsed down to a cylinder, and the boom, which is 9 meters in length, has to have multiple joints and wrap around the spacecraft. So this is a very delicate operation with big pieces of metal and composite structure in order to make this work properly. So it's quite complicated. So first we have to adjust the orientation for proper solar illumination so everything is the right temperature. And then we start the deployments. The first deployment is the reflector. It's released from its cradle, and spring-loaded, it goes out and forms the first joint connection. Then we have a second rotation. Each one of these takes about 20 minutes, and we do one of these per day. So it takes several days to do this full deployment. The bus provided by ISRO is sort of an assembly line bus with special adaptations for our mission. Here's the deployment of the reflector. Spring-loaded again, it blooms, and then there are cables that pull the reflector out to its taut position. All of this, of course, there's only one of each of these things, so it has to work perfectly in order to get this into orbit. So after that, then we go into operations. So this animation is the same one. This animation illustrates the synthetic aperture radar process. So how many of you know what synthetic aperture radar is? Okay, good. This is a cartoon version. It's actually a little bit complicated to explain in detail, and it's also kind of magical in many ways because you can create very high resolution images from a system that you would not imagine could do so. So what I'm going to do is play the animation. So here we are in orbit. This is our satellite, and it's sending these little potato chips, are pulses of energy being sent to the ground from the radar system. It pulses over 1,000 times per second. So the spacecraft is flying along its trajectory and sending these pulses out. So it's going to repeat now. So you can see at the beginning, any given point on the ground is quite fuzzy because of the optics. The beam footprint that's illuminated on the ground from this radar, the flashlight beam, is 10 or 20 kilometers across. So any point on the ground cannot be resolved better than 10 or 20 kilometers. But because we're flying along this trajectory here, each point on the ground, I hope you can see that little green dot, it's imaged over a 10 or 20 kilometer long pathway. So we collect thousands of pulses that have seen any given point on the ground. That means that we can take all of those pulses and adjust them in a special way, basically adjust the phase of each one, adjust the distance, and create a synthetic antenna that's 10 or 20 kilometers long in space. And if you remember optics from when you studied it, the longer the antenna, the better the resolution. So this allows us to get imagery that is resolved down to meter scale, even though our intrinsic ability of the radar is kilometer scale. So that's why it's called synthetic aperture radar. We're synthesizing a long aperture or antenna in space due to the motion of the spacecraft. All right, here's another animation. Now we're going to move into the science objectives and some of the science products that we're going to be creating for NISAR. So one thing we do with this mission is we fly in an orbit that repeats its position every 12 days relative to the Earth. And I'll show you an example of our coverage in a bit. So when we fly over once, we make an image. We come back 12 days later, we make another image. And by using another sort of magical technique called interferometry, we can take those two images, effectively subtract them, and measure the distance that the ground has moved down to a fraction of a centimeter in precision. If we do that over time, every 12 days for a series of months or years, then we can create a time series of the ground motion in 3 dimensions effectively and over in an image format over any place on the Earth. So what you're seeing here is such a time series. This is actually changing as you look at it. This is an area in the Central Valley of California where there's a good deal of agriculture. And in order to water the crops, they pull water from below the ground to irrigate. In pulling the water out, that causes the aquifer to compact and the ground at the surface to sink. So what you're seeing here is the expression of depletion of the aquifer through the surface deformation on the surface. And that's done through using this interferometric technique. There are other satellites in orbit now that can do this. That's why we have these kinds of data. But NISAR will provide much more comprehensive coverage covering all of this other area here. This is important because it's a water resource utilization issue. Water comes from the mountains. You see the snow in the mountains over here. Every year the water melts in the summertime and recharges the aquifer. If you deplete the aquifer too much, there's too much compaction, you get to a point where the aquifer can no longer absorb or can hold the water, and you then no longer have a water resource available to you. So it's a very important water management tool to be able to look at these kinds of things. We're already working with the state of California to monitor this. These kinds of issues exist in India, I'm sure you may be aware, in the Northwest in particular, and many places. Wherever we look with this technique, we tend to see these changes. So a very powerful method. Here's another example of something very similar. This happens to be in the Los Angeles basin. So what you're looking at here, I happen to work over here at JPL, and this is the Pacific Ocean, this is downtown Los Angeles, and this is sort of the Orange County area. What you're looking at here is the Earth, all of the buildings, all of the streets, all of the cars, all of the people going up and down every year by about 2 or 3 centimeters, an inch, as water is extracted in the summertime to water the lawns and water other things, and recharged in the wintertime to replenish the aquifer. So it goes up and down. And what you see here, these orange lines, are the earthquake fault system in Southern California. And you can see very clearly that this motion is controlled by the fault on this side and the fault on this side. So there's incredible science that can be done in understanding the mechanics of the aquifer through these measurements. There's important information about infrastructure itself, knowing where things are likely to be breaking. Pipes may break and streets may crack, buildings may crack, as well as understanding the relationship of water below the surface to the probability of earthquakes. So these kinds of measurements have to be placed in the context in any kind of earthquake forecast model in Southern California. All right, changing gears a little bit. Here's another science product that we hope to make on a weekly basis for NISAR. This is what we call a biomass map. It is basically using a radar, this is a Japanese radar in this case, to create a map of how much biomass there is. The green is high biomass, the purple is low biomass, and the blue is water. This is in the Amazon region, and you can see quite a bit of variability. You can see sort of flooding signatures, which are this orange and red color. And you'll see coming up sometime soon in the video some characteristic fishbone patterns that are clear evidence of logging by people. So here you can see these fishbone patterns. This map took over a year to create. The existing data is not very accurate and not easy to use. With NISAR, we'll be producing a map like this every week or two. That will allow us then to be able to monitor how these ecosystems are changing, helping with policy decisions, as well as just understanding the exchange of carbon between the forest, the ground, and the atmosphere. And last but not least, we have our cryosphere example. So this is an ice cap in Iceland. And what we did is we flew an aircraft system over this from multiple directions, and we could then construct from these deformation measurements velocity vectors that show how the ice cap is moving under the weight of gravity. So you can see, hopefully you can see these velocity vectors moving. The color is the speed of the ice. So the blue is very slow, the red is fast. So there are hot spots that you can tell. These are measurements that we plan to make not just over a small ice cap, but over all of Greenland, all of Antarctica, and also over the mountain glaciers all over the world. So the velocity and the acceleration of the ice is directly related to the forcing functions on them that include gravity, but also precipitation, atmospheric pressure and temperature, and in the case of the ice sheets, the ocean temperature and how it is interacting at the margins of the ice. So these are important measurements for really understanding the impacts of ice on climate and vice versa. I'll skip this one, it's not important. Okay, so that gives you sort of an overview of the science. I hope that was enlightening at some level and enjoyable. So So now I'm going to go into a little bit more detail about what the mission is and where we are with the mission. So this table shows you the characteristics of the mission, some of which I've mentioned already. So we have 2 radars on board, both making images of the Earth. The L-band radar is 24 centimeter wavelength. The reason we picked this long wavelength is that it is less sensitive to the changes of small objects on the ground. So if you have leaves that are moving in the trees, the L-band wavelength is so long that it actually penetrates through those leaves and scatters energy off of larger structures that are more stable. So if you're interested in measuring deformation over a long period of time, then you are better suited to doing that with a long wavelength. Furthermore, if you're interested in biomass, you will penetrate through the leaves, which are low biomass, and scatter off of the trunks and the branches, which are high biomass. So you'll be more sensitive to these high biomass elements. So it's great for that, for many of our objectives. The S-band provided by ISRO is a shorter wavelength, so it's more sensitive to smaller scale structures. Still sees through most leaves, but it's great for agricultural monitoring and looking at low levels of vegetation. So by having these 2 wavelengths, we can extend the dynamic range of our measurements, both for deformation and for our vegetation monitoring, whatever that might be. A great combination. We use a technique called sweep SAR. Given that none of you know what SAR is, I'm not going to say what that is in any detail today, but it allows us to get a full 240 kilometer swath of observation. If we are then in a 12-day exact repeat orbit, due to the way the Earth rotates under the orbit, we can get complete global coverage with a swath this wide. So this gives us a 12-day complete coverage of the Earth. We use a technique called polarimetry. I'll say a little bit about that later as we get to it. And this system has multiple polarimetric modes. We are in an exact 12-day repeat, exact meaning that we come back to exactly the same spot from one time to the next, so we can do this deformation measurement I described before. Our resolution is on the order of 3 to 10 meters, let's say 5 meters amongst friends, which is, given this comprehensive coverage we have, is extremely high resolution for global measurements, and we produce an enormous amount of data, in fact. The mission duration is 5 years, effectively, nominally. NASA only commits to 3 years when they build a mission. They always extend their missions beyond 3 years after the period is over, if it's operating successfully. Given that ISRO's objectives are 5 years and we are partners, we will at least go 5 years and perhaps 10 or 15 years if everything is healthy. The idea is to create as long a time series of measurements as possible so we can track Earth's change as much as we can with this mission. I'm not going to go into these details for you, but we can point the system very precisely, and we can control the orbit very precisely. These are also both extremely important, needed for the deformation measurements. Another unique attribute of this system is the duty cycle. Duty cycle means how much of the orbit the radars can be on in order to be making measurements. Usually there are constraints on data rate, there are constraints on the heat that's generated by the radar in space. The L-band system has been designed so that heat is no longer an issue, and we can basically turn the radar on continuously for the entire observation plan, so we get complete land and ice coverage of the Earth. The S-band radar has a lower duty cycle because of the thermal characteristics of it, but it still covers all of India, all of the surrounding countries, all of Antarctica, and many other places around the world whenever it's needed. We are also pointing to the left. That means that as we fly along in a particular direction, the radar is pointing off to the side, to the left side. Radar must point off of the direction below because of the way radar works, which I won't go into with you. So this is how we look off about 30 to 40 degrees off the vertical. And we are in a 6 a.m., 6 p.m. orbit, which means that we are always, the sun is almost always looking at our solar panels, so we get lots of power, which we need for our radar. So there's a lot of words and numbers on this page, but the takeaway message for you is that this is a really important international partnership, very well balanced with major contributions from both NASA and from ISRO. And you could argue that ISRO's contributions are actually larger than what NASA is doing here, in a sense, in that ISRO is providing the spacecraft bus, the launch vehicle, the S-band radar, and a number of other subsystems for communication. It just happens that the structure size of the NASA contribution happens to be slightly larger than the ISRO contribution. In any case, it's a very massive system. It's like 2,700 kilograms, and it uses 7 kilowatts of power. So it's a very powerful, complex system. I think for you, I might just touch on this. Many of you are in information technology. This part of the mission, this is describing the operations. And I think the salient point here is that we are using pretty high-rate communication systems, first of a kind, to get the data to the ground. And we are using on the US side, we're using complete Amazon Web Services processing, complete cloud-based processing and distribution of the data after the fact. So after we generate the plan and uplink the plan to the spacecraft, it acquires the data. The L-band data is downlinked to NASA's stations, immediately put on the cloud and sent to a processing facility that's on the cloud. And then once it's processed, within a day or two, it's basically moved to another bucket on the cloud, which is the archive and distribution. On the ISRO side, there's another telecom system to send the data to the ground for the S-band data. That goes to the NRSC facility here in Hyderabad and is processed and put onto the distribution system, which is not at the moment on the cloud, but I understand there will be some cloud options potentially in the future. So I'm going to tell you a little bit about the status of the system. We've been working on this since 2014 formally, and in around 2019 to 2021, we started to have all of the boxes, all of the sub-assemblies being put together, integrated together into bigger sub-assemblies. So all of that work is done. The instrument structure was integrated at JPL. The S-band electronics was shipped from India to JPL, integrated all together. We shipped it back to India last year, and so now we are in the process of integrating that structure with the spacecraft itself. That's going to go into its thermal vac activity shortly, and then we will launch early next year. So we're getting very close to the end. Here's just a few colorful pictures to give you an idea of what we are building. This is the spacecraft and reflector and boom in a thermal vac chamber back at JPL before integrating with the spacecraft. This is actually not the flight model for the instrument. It's the flight model for the boom and the reflector, but the instrument is just a look-alike dummy. This is the actual flight system in August 2022. So you can see it's a pretty complex structure. This is after all the testing there. We packed the whole thing up, put it into a big box, and shipped that big box on an aircraft to India. There you can see the box inside the aircraft. And then it came to India. This is when it landed on March 6th of this year. And now it's at the iSight facility, integration facility in Bangalore. So it's coming soon. This is what it looks like the last time I saw it back in March or June of this year. This is the instrument electronics. This is the spacecraft bus, all integrated together. They've gone through all of their compatibility testing, and they're now getting ready to test it in the flight environment. So we're planning for launch in early 2024. We expect to have images a couple months after that, 2 to 3 months after that, and we expect to have science operations at the end of that 3-month period for as long as the mission lasts. We have these global products. I haven't said much about the products, and I don't know how interested you are in them. So I will either end here, or if you say, yes, talk some more, I will continue talking because I have more slides on this topic. But there will be high-level products, first-of-a-kind products that are freely and fully openly available to the global community. So as I said to another group earlier this trip, I think as students of remote sensing and information technology, this is a real opportunity for you. These data sets are going to be extremely rich, completely unique, especially over India. There will be L-band and S-band polarimetric data every 6 days, effectively, ascending and descending parts of the orbit every 12 days. You will get an amazing time series of change over India over the life of the mission that is not possible to get by other means. And so it's a real opportunity for you to explore. As I hope I convinced you, there's a lot of scientific and applications value. And at least on the NASA side, there's a lot of data tools and services that will be provided to all of our users internationally to be able to access the data conveniently. So it is 5 o'clock, so maybe that's a good place to stop, or what should I do? Should I continue on a little bit? On the data part, okay. So I'm going to continue on just a little bit. Sorry for those of you who are captive here. Okay, so just to say a few words about the measurements, polarimetric measurements. We transmit an electromagnetic wave with a particular orientation of the electric field. We can transmit horizontally, and the radar can be designed to receive that same polarization or the orthogonal polarization, vertical polarization. So we can either transmit one and receive one, or we can transmit one and receive both. And then on the alternate pulses, we can also transmit on the vertical polarization and receive both. So we can create a complete set of polarimetric states from alternating back and forth this H transmit, V transmit, H transmit, V transmit on these pulses. So that's how we create polarimetric data. And the polarimetric signature of a particular ground element, a scatterer, is related to its geometric properties primarily, its orientation, whether you have a building with a corner associated with it or a canopy with random branches and leaves, they will have very different polarimetric signatures. You can see, hopefully you can see in this image, this is a wetland area in California, and the colors here are representing different scattering mechanisms. The green are vegetation, the reds are surface scattering, and so forth. So you get very clear signatures of different kinds of scattering mechanisms on the ground. And by looking at these signatures evolving over time, you can then measure changes to those surface attributes. So that's what we do with polarimetry. You can see the list of possible targets. This is what we use for our biomass estimation. Basically, the brighter the return, the more biomass there is. That's effectively how we make that measurement. For the interferometric method, where we take one image and subtract the phase of the other one, what we're doing is looking at this path length as measured in wavelengths of the radar. So it's a coherent system. We effectively transmit on one frequency. So if the ground moved from one time to the next, this ground has moved, then we can actually measure in that difference this wavelength change, this wavelength distance change. So here's an example of an earthquake signature where as you go from one color through the color wheel to another color, you've moved on the ground by around 3 centimeters. So it's a very, very sensitive change to very small motions on the ground, as I showed you with those animations. So we use this for earthquakes, volcanoes, landslides, other subsidence effects, and all of the ice sheet monitoring. This I already talked about, so I'm going to get to the data part. Okay, this just shows you our observation plan. I think I mentioned that we get full swath every 12 days, allows us to get complete coverage. So we're planning on covering all of the land and ice covered surfaces of the Earth every 12 days from the ascending part of the orbit and the descending part. So it's effectively sampling once a week. And the colors here are just telling you different modes that we're going to operate in. And the actual modes are not all that critical. But you can see that because we make this measurement every 12 days for the life of the mission and the resolution of the system is fairly high, we end up with about 1.6 petabytes of raw data per year. And once you process that through the cloud-based processing system in our case, that increases to something like 30 to 50 petabytes per year. So it's a lot of data, not something you want to download to your laptop, probably. So cloud processing makes a lot of sense. These are the modes that I think probably we don't want to go into too much detail. Okay, so let's get to the data then. So unlike many synthetic aperture radar missions, which will deliver to you either raw data, which because it's not processed doesn't look like anything and is kind of useless to most people, or they'll give you this so-called level 1 data in radar coordinates. Radar coordinates are different from your normal image coordinates because you look off to the side and you're measuring the distance, the range off to the side, so everything is distorted in that range image. This is typically how data are delivered to users, and the SAR developers wonder why nobody wants to use the SAR data from these systems. So we took it upon ourselves to change the methodology, change the paradigm, and create geocoded products that are you can take and stick into your Google Earth engine and just lay it right on top of it, and it should be co-registered with a planimetric grid. So that's a new thing for NISAR. This is being done both for just these so-called single look complex images, which doesn't mean anything to you, but are the fundamental measurement from a SAR system. And it applies to our interferometric products. So to create an interferogram, as we call it, we take one image from the first time step, the other image from the second time step, and we cross-multiply them with a conjugate. So that gives us then a phase difference, and this then gives you the phase difference. This product, this one happens to be in the radar coordinates, but this will also be geocoded. So you'll be able to take the geocoded time series of data products and track the deformation with relatively straightforward algorithms. You don't have to do the hard work anymore. We have a so-called DAC. This is a Distributed Active Archive Center. That's where we store our data. It's called the Alaska Satellite Facility. If you use any radar data in your research, I think a few of you do, this is where you'll probably be pulling the data from, the Sentinel data, and NISAR data will also be at that DAC using the same search query interface. So it'll be very convenient. Most of the world goes to ASF to get their SAR data these days. This is a detail that's beyond what I want to talk about, but I did want to mention that we do produce actually 2 images for every observation. We produce a full resolution image that is the main workhorse of your research. We also produce a lower resolution image in range. It happens to be separated in frequency by some amount from the first image. The reason we do this is because we propagate through the ionosphere, which causes some errors in our measurement, and we want to correct for that. And this allows us to do it. I'm not going to go into the details of how we do it, but I'll just say that an interferogram might look like this. All of that signature practically is ionosphere, not the ground deformation we're interested in. Using this technique I just described, we can estimate the ionosphere and remove it. And we're left with just the ground deformation. So with NISAR, we're going to be able to do a factor of 10 better than existing systems. So a very powerful technique. Another product that we're going to be producing is also a first of a kind. This is called a radiometrically terrain-corrected product. Again, because we look off to the side and there might be slopes tilting up towards us or away from us, the radar brightness will be modulated just by virtue of the slope effect. And that's not tremendously interesting from an interpretation point of view. So what we want to do is remove those terrain effects and leave the intrinsic reflectivity of the surface in the data. So here you can see a couple of examples. This is in Los Angeles, this is in Peru. You can see these bright and dark features are the effects of the slopes in the Los Angeles area. After applying this correction algorithm, you can see all of that slope effect is gone and we get the intrinsic reflectivity of the surface. Same here in Peru. This is also quite flat now. So these will be produced globally. These are level 2 products, geocoded at roughly 20-meter resolution, available to you for analysis. These will be smaller than the full resolution, so these you might want to even download and use yourself. I think a couple more slides and then we can end. We have, this one probably is not all that interesting. I'll skip that. So as I mentioned, we have a cloud-based system. It's really kind of innovative in the sense that we have the archive and the processing done by 2 separate organizations using the same cloud-based infrastructure. So effectively, once the data are processed using the processing system, they are probably not even moved. They just have a flag flipped that says, I am now in the archive. So there's no data movement from going from processor to archive. So a very efficient system. We work together very well with the Alaska Satellite Facility to make this happen. The other thing that you may be interested in is our open source approach to everything that we're doing on the project. We have all of the software that would generate those products that I just described to you. All of that software is already available to you on the web, on GitHub. It's called this ICE3 software. You can click on that link and get access to that software. It's the same software that's going to be used in production. So if you don't like what we did with the selection of parameters for processing, you can change the parameters yourself and reprocess it as you wish. In addition, we are creating higher level science products to validate the mission. These are specific to the mission, but they are templates for how you might want to do higher level processing yourself. They involve time series in many cases, thresholding, other kinds of algorithms. These are also on the web and available to you. So you can download those, use them with data that is provided free also, and you can exercise your understanding of the algorithm, and once you're comfortable with that, reproducing the results the science team has done, you can take that and apply it at some other place in the world to do your science. So by virtue of this, we're hoping that users will feel comfortable with the algorithms and not have to feel like they need to generate everything themselves. We also offer a lot of training opportunities just through the normal NASA training process, but also through the project. The Alaska Satellite Facility is keen to develop new users. They have a tool called Open Science Lab, which is a cloud-based resource for training, and they have a number of online courses that they offer. So bringing geoscientists to the cloud to process is a big hurdle that NASA would like to overcome. You are the generation that will be able to do this and hopefully will do it. And these tools, we hope, will facilitate that. So now I really will end. And this is the final integration phase coming up. There's a lot of work to do still, especially to get all of the products seamlessly created, both between NASA and ISRO. They have to work together and look the same. But we'll have these global products at level 2, cloud-based tools, and very excited and engaged community. We hope we'll be ready for the data. So that's it. Thank you very much for your attention. Appreciate it. And I'm happy to take questions. Yes. Any questions you have, please. Yes. I would love to say it's the first step for gaining control of our planet, but I'd say it's a major step. Of course, there's many systems in space right now, but many of them don't have this kind of comprehensive coverage in space and time. So it's a major step.
And so, like, how it is related to the Gaganyaan mission, because that is also in process.
Isn't that a human mission?
Yeah, but like it is also the same goals. Like climate change.
No, I think they're going outward, not looking inward. Yeah. They want to populate Mars, and the Moon, not fix Earth.
So, what are the
Thank you.
what are the applications with respect to atmospheric weather related problems?
Yeah, so one of the things I skipped over was some of the noise sources in the measurements. So when we make the interferograms, actually I can go back and show you here. So you see this, I said this is deformation. Actually, most of this is probably residual tropospheric noise. Basically, the wet troposphere is turbulent and it creates a path delay to the radar that's very difficult to correct. The way that we address it with our nominal science is by taking a lot of time steps and basically filtering it out relative to the deformation. However, each one of these is data in itself for somebody interested in weather. So we've had many workshops and discussions with weather modelers to see how these kinds of differential measurements every 12 days could be used as coarse boundary conditions to improve weather models.
I have another question. Like today we have so many different types of systems, satellite imageries. If this is coming out with a higher resolution, then some other previous mission takes a back seat because of spatial resolution or the temporal frequency. Won't this lead to erroneous decision making with respect to policies? Say, for example, day before yesterday there has been a tsunami in Japan. There has been an underwater landslide. But there was a policy decision that earthquakes below 5 Richter scale is not going to trigger a tsunami. But still there was a tsunami. Now, like there's so much of mismatch despite having so much of data around. So how do we even tackle and work around all these things?
Yeah, that's a huge question.
Yes.
And some of it has to do, and this is sort of my opinion, I'm not really an expert on policy to remote sensing, but that said, a lot of the issue is with the data products themselves. Often they are, the errors are not quantified. So people don't always know how good or how bad the results are. And there's a lot of pressure to provide data products in order to make decisions. I think, so for NISAR, it hopefully is a regular, reliable, and well-quantifiable set of data. It's not subject to cloud cover because it's a radar, it sees right through the clouds. We're not taking data randomly, we're taking it regularly, so we should be able to intuit from the temporal changes what's actually happening as opposed to what we think is happening. So I think that kind of regular observation cadence and comprehensive coverage will help to reduce the error rate of interpretation. It won't be perfect. No system is perfect, and we need to be as diligent as we can be in quantifying the errors, which are also difficult to quantify because the noise of these systems is not simple white Gaussian noise, zero mean, right? It's complicated noise. So we need to be honest, and we need to provide the proper interpretation to the decision makers. The fact that systems have different resolutions and different capabilities, that should not be an impediment to using them all, as long as we properly characterize their benefits and limitations. I think that was a political answer to your question, so the best I could do. Yeah.
Hello, sir.
Yes.
So you've mentioned how SAR is effectively the satellite moving over a particular area, allowing it to form a larger aperture. So
Correct.
is this similar to how the Event Horizon Telescope took the black hole image? Because even there, like multiple satellites were focusing on a particular area, I mean the black hole from across different regions across the globe. So is it related, or like is it a different methodology?
So I'm not familiar with what the technique for data reduction there was. Was it interferometric, optical interferometry? Optical interferometry. So interferometry is slightly different from what we're talking about here. This is more classical optics, but you know, it's all related in some fashion. It's all physics. But so I think the answer is no, it's not the same technique. Yeah.
Sorry, a cynical question. How many single point of failures does this mission has?
Is that a cynical question?
Could be because it is regarded in India that you are not supposed to ask negative questions. But I just want to know because this interests me because the recent launch of the James Webb has somewhere around 500 single point of failures. So based upon that, we could know the criticality of the system or the criticality of the integrated system.
Yeah, so first of all, you should not be embarrassed about asking it, and it's not cynical. It's an excellent question, and it's something we obsess about continuously as we develop these missions. So I'm sure we have many fewer than James Webb. We have the reflector and the boom, definitely. We have the launch vehicle. That's a single point failure. Everything else on the system is either redundant or gracefully degrading. So for example, for the radar systems, we only have one L-band radar. And our objectives on the NASA side must be met using the L-band system because it needs global coverage, and the S-band system can't make global measurements because of the thermal limitations. So we know that we're relying on the L-band system, but there are 24 transmit-receive modules, 12 for each polarization, and there are 6 processing units that take those received signals and process them. Those are also 3 per polarization. And then there's 2 polarizations. And so we can lose a TR module and have a small degradation to performance. We can lose one of those 3 processing units and lose a piece of performance. We can lose an entire polarization and still have the other polarization. The same logic applies to the S-band system. We also have 2 radars. So for at least over India, we've got lots of redundancy from that perspective. And then on the downlink, we have 2 downlink systems. And we have 2 flight computers, 2 radar controller computers. Everything is at least redundant at some level. The only other main single point failure that I can think of is the gimbaled antenna for the telecom. We have two telecom systems, but only one antenna for both. So if that one fails, we can't get the data to the ground. That would be a problem. So it's not too bad, I'd say.
So after launching this, you'll be having, we work on Sentinel-1 currently. Do you have any way where we can collaborate on having this data and checking it and how it improves our existing process? We do biomass estimation and some surface bathymetry studies. So can we try out this data and then see how better it is?
So the data will be placed in the DAC within 2 days of acquisition, fully processed. And you will be able to go to the ASF website and draw a bounding box around the area of interest and pull the data. So in that sense, no collaboration is necessary for access to the data. You just can get it.
Even S-band?
So the S-band data will come from ISRO. And it is open and is free. The actual mechanism for getting the data will be through Bundini, and my understanding, I am told, is it will be a very similar process to what's going on with NASA, but I have no control over that. There is a hope that the S-band data will be mirrored at the ASF site, and also, of course, over India. Any place that we're taking L and S-band data together, all over India, Antarctica, surrounding countries, a few other places around the world, that's all jointly required L and S-band data. Any place where that's acquired, the L-band data, which is being processed at JPL, at NASA, will be provided quickly to ISRO. And in fact, ISRO's plan is to process the L-band data themselves. So they will get the level 0 data, the unprocessed data, from us, and process it themselves and produce an L and S-band joint product. The latency that they are quoting is the same as our latency or better. Generally, ISRO has a very quick turnaround for creating products, less than a day usually. Again, access to it is not my job to state. But let me just put it this way. I don't mean to be flip about it. There is a strong desire since the first day we met with ISRO for this science mission to have the data be open and available for both S and L band. So as far as I know, ISRO's plan is to have us go hand in hand with data availability.
I am very interested in understanding like the perspective of like how, what is it like to work on
Thank you.
a huge project that takes like decades to do and to run and then like have like one attempt at it and like without failure. It's such a huge unique experience. So like what is it like?
It is at times it is the most frustrating thing in the world, and at other times it is the most uplifting thing in the world. The way we build missions at NASA is very process oriented. So everything is designed from a requirements flow down perspective. The science requirements are written down and codified, and then a bunch of system engineers get together and say, okay, this is what the science is. How are we going to build this mission to meet those requirements? So there's years of paperwork and meetings just to figure out what the system needs to look like. And then you have to validate it as you're building the hardware. You have to build the hardware. It's actually an incredible process. But it's often done by people who are discipline experts in their area but don't have the big picture. So it can be quite frustrating trying to explain to people why things need to be the way they have to be. But it's hundreds of people, and they come and go in the project. I've been here since the beginning, so I feel quite enlightened and quite thrilled that we are so far along in getting ready for launch. I've had 3 main projects that I've done that I consider to be the cornerstones of my career. I worked as a graduate student on the Voyager spacecraft, which was flying by the outer planets, and did some work on those data. It was amazing. I built the SRTM topo mapping system. I was one of a team building that system. That was an amazing mission. NISAR, I think, is in many ways the peak, the pinnacle of that, because of the complexity, the need to coordinate 2 organizations with completely different space cultures over a period of 10 years. It's been an incredibly rewarding experience, and I've learned an awful lot from the whole process. I hope that answered your question.
Hello. Yeah. So seeing as you work with multiple, like for this project, you had to work with multiple different systems and organizations and various teams of different disciplines. What would you think would be very important in trying to get them to work together without having one system, one discipline build something and another build another, and then having compatibility issues between them? Right?
Yes.
Any
So
tips on resolving something
it's
like that?
called system engineering. That's the whole purpose of system engineering, is to set up the requirements in such a way that that the requirements themselves ensure compatibility. The problem is that we're all human and we do make mistakes. So we typically need to document and then discuss. And sometimes there's no time to do the discussions. But there's really no substitute for system engineering. The whole process of requirements flow down, starting with the science requirements, figuring out what the mission needs to do, figuring out what the instrument needs to do, figuring out what the subsystems of those instruments needs to do, all the way down to the board level for the system. And this is done for electrical as well as mechanical systems and mission systems. All of it it's very complex, and that's why they're often very expensive and take a long time.
Would this be the most time-consuming aspect of such a undertaking?
Yes, I think it is. And different organizations approach it differently. Some organizations rely on the expertise of their engineers to be system engineers and just sort of know what the right thing to do is without all the documentation. If you do it that way, you can do it much faster and still get the same result. But not every organization does it that way. And that's certainly not the way NASA does it.
So you mentioned that there are 6 processing, towards your light.
Thank you.
You mentioned that there are 6 processing units in the spacecraft, and like the images that are to be sent to the Earth would require some part of that processing. But what other processing happens in aboard the spacecraft, and what happens on the Earth?
Yeah, good question. So the processing units on board have to take the individual sampled signals from each of the 12 TR modules in each of the polarizations and combine them in such a way to reduce the data rate by a factor of 64 relative to the initial sampling. It also has to do digital beamforming. So I don't know how much time we all have here, but let me show the slide that I skipped over, which explains kind of that. Here, this one. Oops, that's my Python work. That's not what we want. Okay. I don't want to join EduRoam. There we go. So these are the radiating elements on the system up here. Sorry, this is not doing what I want. These are the processing units. So here's a block diagram of what we have here. Each of these transmit-receive modules, they receive the signal. It goes into this unit here where there's analog to digital converter on for each of the received channels. That is sampled at 240 megahertz. I don't know if you know anything about radar electronics, but typically the signals are filtered, and then they move the center frequency down to a much lower frequency, and then they sample at a low frequency to keep the data rate down. In this case, we direct sample a 1.25 gigahertz signal at 240 megahertz. That digitally moves the signal down to a lower bandwidth that then needs further filtering to get down to the usable band for each channel. So that's some of the processing, is that filtering. The next stage is to take, here, let me start this animation again. So you can see the way we operate this, we transmit, when you see this red here, hold on, that red transmits on all TR modules at once. It illuminates a narrow region on the reflector, which then illuminates a broad region on the ground. Then the signal, the pulse propagates to the ground. It's compact in space, each pulse. It's transmitted for like 30 microseconds. It reflects off the ground, comes back to the radar. That signal spreads in space and reflects off the entire reflector and is focused down to a particular spot on the receive element. So it's received by 1, 2, or 3 transmit-receive modules at once. And it's sweeping across that at the speed of light because the wave is traveling at the speed of light. So that's what's illustrated here. Each of these beams here is digitally tracking the position of the echo on the ground. So since it's hitting multiple receive modules at once, we have to properly weight and sum those 3 signals to create the net signal that can then be synthesized across all of the whole beam. So the filtering, the digital beam forming, further filtering, that all leads to, a teraflop worth of computation. And that's just to process the pulse, to get the data rate down. Then we have to downlink all of that data and process it into an image. So that synthetic aperture radar process I described earlier in a cartoon requires basically either FFT-based convolution approaches, or in our case, we're doing direct back projection processing of the data, which is computationally intensive. And then beyond the image processing, we create the interferograms, the radiometrically terrain-corrected data, and the other products. So that's the difference between the flight processing and the ground processing.
Okay, and you mentioned while deploying the spacecraft, it takes about several days to finally open the aperture and just operating 20 minutes a day. Why is that the case in spite of it being a 6 a.m., 6 p.m. orbit where sunlight is always available?
Yeah, good. I've asked that question many times. It's because of caution. They want to make sure that they fully understand all of the signals that come to the ground. There is no, high-resolution video camera up there looking at what's going on. So they have to infer the health of the system through measurements of sensors that are placed all over the system, particularly accelerometers and current and voltage sensors. So you would think that after 10 years of development, there's a little tool that would take these data and they could just hit a button and get a result out that says it's healthy or it's not healthy. Yes, I agree. But they would like at least a day to do it. Maybe there's a particular time of day that they want to do the deployments, and so once they do it, they want to just wait till that happens again, but I think it's just caution, really, nothing else. It can't. Viruses? What kind of viruses? Oh, zombie viruses due to climate change. So the system can't do anything about that. However, it will measure the changes in the ice sheets, and if we suddenly see that the ice sheets are melting, then probably the zombie viruses will wake up. So, yeah. No, it's not going to directly impact that. Okay? Great, thank you.
Thanks a lot, sir. The talk and the animations were very enlightening. We hope all of us will avail the resources, data sets, opportunities to upgrade ourselves further as well. So, as a part of IIIT Silver Jubilee celebration, it's our pleasure to host you here today. Now, on behalf of IIIT, we also wish the best of luck and best wishes for the launch next year. I would like to request Professor Rajan to come on the dais and hand over the token of appreciation to the speaker, Dr. Rosain, and also to Dr. Naresh from NRSC for supporting us.
Dr. Naresh is from NRSC, has been, I think, the primary coordinator.
So,
has also
yeah.
been the past chair of IEEE GRSS in Hyderabad.
Dr. Naresh is the reason we are having this talk again. Thank you.
Hello everyone. It's always a pleasure and delight to listen to Dr. Paul. I've been with him since 7 years, more than that, possibly. And be it science, be it process engineering, or be it systems engineering, or requirements. These are very much required in space science and doing this kind of development. And kudos, today we have NASA and ISRO coming together, launching the NISR, and we will be doing a good job and coming up with beautiful products of both L and S band. And message to you is that try to be, using all these data sets, develop new IT tools, and as you know, the space sector is growing, and the open geospatial policy has come up, and we want each one of you to use the data sets that will be put onto, as Paul was also saying, it will be on Bunidhi portal for our data sets, and also on AWS. So try to use and develop new applications, new ways of looking at the Earth system, solid Earth, as well as do very good applications out of the remote sensing data. So thank you so much to Dr. Rajan, Professor Ramesh, and your director, IIITH, for having this talk here. And thank you once again. Thank you.
Last but not the least, thanks audience for being here and for the lovely questions that you asked. I hope it was a helpful talk for all of you. Please enjoy the high tea outside and have a good evening.